Who just wants to have a beer? Okay. So we have evolution, and who believes in robots? Who believes that robots exist? Who is a robot? Okay. That's something that I always learned. My first sentence in English was, I'm not a robot. You can use it on very many occasions. Well, so that's the two ingredients for the next speaker, evolution and robots. I want a big round of applause for Evert Haasdijk.
I'm Evert Haasdijk, I'm a nerd. And more specifically, because I can't juggle. So I'm half developed. But I might be able to do the robot juggle. Sorry, we'll have to see. I want to talk about robots and evolution, and first I have to explain something about how we view evolution in robotics. And we use something called evolutionary algorithms, which is it's actually a generated test method of searching. So you try something, and then you see how it works, and then you tweak a little, and then you try it again, and then you see how well that helped you, and if you say this goes the tweak away, you try another one. And the reason that we call it evolutionary algorithm is because we borrow our ideas from biology, from evolution. So we don't talk about a set of solutions or candidate solutions. We talk about population of individuals, and individuals mate, and there is crossover, exchanging genes, and genes mutate. They're just, in the end, they're just numbers that change, and then we try how well the numbers work. This being nerd night, I thought somebody should have some pseudocode on the screen, so I volunteered. And this is also the standard obligatory bit of pseudocode that you get when you start when you do a course on evolutionary computation. So, like I said, it's a generated test method. So you try to first generate some individuals, some trial solutions for your problem. Then you see how well they work by trying them out, and then you combine the ones that work better than the other ones in some usually stochastic manner, and then you recombine those. I'll show in a minute. You recombine parts of the solution, and you mutate them by keeping changing them a little bit more, and then you see how well the result of that works. And if it works well, then okay, you learn something. And it's used in many different areas. And I'm just to elucidate the concept, I was talking about this satellite. It's Mars Voyager, and there's a little antenna at the bottom. It's a very tiny little thing, but it's crucial because it's what it uses to communicate with us here back at Earth. And this antenna, the design of this antenna was made with evolutionary computation, with an evolutionary technique. And the way that works is fairly straightforward. The parameters of the antenna, the width, the height, the number of twists that are in there, the number of coils, is encoded in a string, so it's just a string of numbers really. And we have a population, a set of candidate solutions, we call it the population. And the population, we try all the various trials that are in there, the various candidates. And the ones that are better than the others, they're still crap in the beginning, but the ones that are better than the others, they get to procreate, just like us humans, the better ones get to procreate. And so suppose that in this particular set of candidates, there are two have been selected by whoever runs the algorithm to recombine. What happens is very straightforward. You take a couple of numbers from the one, a couple of numbers from the other, join them together, and you've got a new solution. And then, well, then we have mutation, which happens right here. You can see maybe you saw, maybe you didn't. There was one of the items changed a bit in value. What you do is you just add a bit of random noise to some of the values, and that gives rise to a new form of antenna, a new shape of antenna. You try that, typically, you try that in a simulator, and because it's very difficult to build those. Although there is an example of a guy who was doing nozzles, so it's not, but he actually built it because he couldn't simulate it properly. And if it's any good, then you store it back to the population and you start again until you're bored, you run out of time, or the antenna is good enough. So that's evolutionary computation, and it's used in quite a few industries. It's used in planning, for instance, for planning rosters at schools, for parameter tuning. If you have some incredibly complex system that you don't understand, you can tune the parameters of that. It's used to design, as we just saw, it's used for design of antennas, of robots, of many things. It's used in data mining, and trying to find correlations in databases that allow you to do predictions about, for instance, customers going to another company, or if you're a bank, people repaying their loans, their mortgages, things like that. If any of you have a cell phone with an orange ornament, then it's very likely that they use something that they built with a GA that I actually wrote. That they used an evolutionary algorithm to rate the likelihood of you staying on after the lease expires, and the likelihood of you actually paying your bills.
How do you morally feel about that? That's wrong sometimes.
Well, yeah, but then they're right more often than if you just ask an expert. So that's it's not as bad as it could be. So how does that work for robotics? Well, typically what happens is you have a little robot like the one you see here. It's called an EPA, and you have a top of the line computer that generates the parameters for the controller. Typically, the controller is like a neural net, just a very complex equation that takes the input, the sensory values from the things that the robot sees and feels and does, and tries to calculate how to set the wheel speed, for instance, for that robot. And the computer generates all these values, all these individuals, sends them to the robot, and the robot runs around with them for 10 minutes. And then you note how well the robot did. Maybe you did it in simulation. You note how well the robot did, and that's the quality of that solution. Rate all your solutions, and the better ones get appropriated. You get new ones. So that's how it works. And in practice, a guy called Lipson, quite famous in our field, he did this. He did this at Cornell. One of the many people. He's one of the ones that have a video on his website, which is why I mention him. And he has this. He has this quite odd-looking robot, which is in a basin. And the task for the robot is to learn to walk. That's where we all have to start at some point. The robot has to learn to walk, and if you at the top here you see a video camera looking down. Actually, what it does is it measures how far the red ball proceeds along the floor. And you'll see in a second, you'll see in the videos, you'll see excerpts from the robot during the evolution. So in the beginning, it doesn't walk very well at all. But towards the end, as evolution progresses, it learns to walk just as we learned to walk at some point when we weren't fish anymore. So there's the video. Don't you? But this is only, so this is just four iterations. It's already, it's going somewhere. Still there? 20 centimeters a second. I challenge you.
So each set of legs
actually can't rotate, right? You just
No, they're just pistons between the triangular things. So this is those are the guys that actually did it. So it's not my credit. I just told their video. So this is all very well and interesting and cool, but it's child's play because look, where it's at modular robotics. So what we do in the project I'm working on with lots of other universities called the Symbiotic project, we build these robots. I say these robots, but there was one until a couple of weeks ago, and now there are 3. But the thing that's really cool about them, once we have enough, is that they can hook up to each other. They can link to each other. These robots can drive around individually. They can find their friends, and hook up to them, and then form an organism of whatever shape. So they can form like a hand or something. Because they can, in the middle you can see a hinge, and they can move like this, so you can build all sorts of things. Well, so I can't show you a proper video like I showed you for robotics work, because we don't have the robot yet, but we did do some trials in simulation. And then what you could come up with is something like that should play like this. You know? Yeah, just good. There it is. Isn't that awesome? And this is sort of towards the end of a run of evolution. But nobody told this robot how to walk. We just said, the only thing that we ever did was tell it, you moved so far, that's better than moving less far. And the main difference with the robot that we showed just now with this is actually 14 robots. It's not one robot, it's 14 robots that are linked together. And the 14 robots all operate independently of each other. And the only thing that they hear from the robot that they are connected to is, I think I'm going to set my angle, my hinge to this angle, and they react to that, and that enables it to walk. So that's all really cool, I think. But then I'm a nerd. Oh yeah, we all are. Okay, so that's all really cool. And what happens is that the robot feeds back into the computer all the time. In this case, the simulation feeds back into the other program all the time, telling us, telling where it's at.
is that why he's broken?
I can't comment on that. Spectacular failure. You can see just giving up. Oh. And the wires is for the power. Because the other things, naturally, they run out all the time. Okay, so that was that. So that's to combat one of the challenges if you want to do online learning, if you want to train on the job, is to have a good sense of yourself, to have a sense of what your body or what the robot is for her body looks like. And what we are trying to do, and this is I'm going to end with a little movie that's actually a demo. Really cool what happened there. And what we're trying to achieve is we're combining all these things into this. So these are all individual robots, these little blocks. You can see them shaping up into little bodies. Now they get into trouble because now they reach this huge canyon. Fortunately, help is at hand. But En look, it's Lange Jan daar vrij.
En deze kijk.
Okay, so that's what we're trying to achieve.
Thank you very much, Evert. So the ones that don't get a job at Transformers, they end up at the Ministry of City Works.
That would be a good thing.
We get quite some good jobs for them.
Yeah.
Any other questions for Evert from the audience?
Yeah, I mean, you've got lots of stories of revolutionary algorithms and idea from biology, but with us now sort of developing technology in biotechnology, you've got Craig Venter, which is the human genome project. He's working on sort of like artificial algae, and then like the genome of algae to produce crude oil from gases. Do you see us like taking this technology back to biology and actually applying with increased computing computational power and things like that? Actually, sorry, I know it's nerd night. Yes, you can. Just see us actually applying back to biology to actually do bioengineering.
Yeah, I can paraphrase your question just for the people in the back.
Sorry.
Can we apply this in real-time biology? Is that your question?
Yes.
Yes, actually, and actually that's being done.
Okay.
It's actually, there's a guy, I forget his name, he's in Cambridge, and he tries to build DNA computers using techniques like this, with proper little DNA strings. It's really cool, and I don't understand how it works, but it's
How small can you make it? I mean, what's
well, DNA is sort of the smallest.
Yeah, so it still has the same learning algorithm, it still has the same memory, and how long is learning about?
Well, no, I doubt that you have DNA with an internal representation of itself, but
if it knows how to move one direction, if you say change the path, change the target, I mean, it still has some memory, set it itself, and
I can't really speculate on that really.
yeah. One more thing, just for your case, how many detectors do you have to sense the movement of the spectral ground or whatever they call all the parts?
The question is, how many detectors does it
How
have?
many in the example that I showed you with the starfish, I think it only has 4 sensors or something. Well, externally, internally it knows it can sense at angles, so there are probably 2 sensors for each joint.
So now the algorithm just calculates with respect to like how each taking account how each part is, so just
Yeah.
actually detector, right?
I've done
It's equation or something.
That's it. No, it's just my self-checking equation. Wait for an equation.
What's the memory from? Like,
I don't know. You have to ask me.
Right, so I think we have a Dr. Evil in the audience who wants to build his own supervisor. So, right, well, let's thank our second speaker, Evert.